Hello, class of 2018. You thought you were rid of me, didn't you? I need to tell you a couple of extra biostatistics topics that we didn't have time to teach in EPH first year. Your class is sort of the only class affected by this because we got extra biostats time put back in the curriculum for this year's first years. But I realized that we ended last year's class without me being able to give you a little bit of information that I think you might need for the board step 1. So this is just an extra webcast for you to get that, and you can review it later closer to the boards if you want to. What we're going to discuss briefly are a few things, again, that we didn't get to in first year EPH. One is just some theoretical language about alpha and type 1 and type 2 error that really we've already discussed the concepts, but I just want to make sure you know the proper names for things because I think that will be asked on the boards. I want to briefly cover non-parametric tests, which again, I think you only need to have a nodding acquaintance with this for the boards, but I'd like to just, sort of let you look at the names of them. I want to talk about survival analysis, which I mentioned briefly in EPH first year, but we didn't have time to do it. And then briefly also talk about intent to treat versus per protocol analyses, which might be on the boards and is also an important thing to know for when you read journal articles. So first, I just want to go over some theoretical language that's in most all the statistics textbooks. And again, we talked about this briefly at the beginning of the biostats lecture, but I didn't belabor the vocabulary because I just thought it would be confusing and we had so little time. So when you are about to apply a statistical test, you always think in terms of the null hypothesis versus the alternative hypothesis, or H0 versus HA. Most of the time that 0 and A are subscripted. I couldn't find the subscript tonight on my PowerPoint, and so I just proceeded without it. The null hypothesis means that there's no detectable difference between the two groups, or in other words, the intervention did not work, or at least we cannot say from these data that it did or didn't work. The alternative hypothesis is basically the opposite. In other words, there is a detectable difference between the groups. So most statistical tests, when you go into the testing process, assume the null hypothesis to be true, and therefore the bar to reject the null hypothesis or to prove the alternative hypothesis is usually fairly high mathematically. And alpha is the probability of rejecting the null hypothesis when the null hypothesis is true. In other words, the probability of mistakenly rejecting the null hypothesis. This is usually set at 0.05, which you may recall that when you read articles, usually p less than 0.05 means it's significant, and this is sort of the parallel language for statistical testing. So in other words, if you reject the null hypothesis and you have a p less than 0.05, then that means there's a less than 5% chance that your finding is a false one. So that's the way to think about the 0.05 in terms of statistical language. I also gave you some language about sort of what it means epidemiologically. Like if you've repeated this experiment 100 times in this population or a similar population, you would find the same result 95% of the time. That's basically the same thing, and I find that easier to grab onto, but just so you understand what alpha is, it's the probability of rejecting the null hypothesis when the null hypothesis is actually true. Excuse me. So remember that we talked about error versus bias. We spent a lot more time on bias in first year EPH because frankly it's more interesting. Bias is when you design your study in such a way that you wind up with a skewed sample in some fashion that sort of drives your results in one direction or another away from the truth. Statistical error is just like random error, the probability of finding a false result. And there's two kinds of errors that we talk about, type 1 versus type 2 error. I find this language to be a bit clunky, but I do know that they ask about this on the boards, or at least they did last year. So type 1 error is the incorrect rejection of the null hypothesis when the null hypothesis is really true. So one way to think of it is a false positive result. So you found the alternative hypothesis, right? But the null hypothesis was really true. So in layman's terms, you think that you found a significant difference between your two groups, but there was really not one. And again, if you position your alpha in the right place, your likelihood of having a type 1 error is probably 5% or less. Type 2 error is an incorrect failure to reject the null hypothesis when it really should be rejected. In other words, a false negative result. So you found the null hypothesis, but really the alternative hypothesis was true. The other way to think about this in layman's terms is there was really a significant difference between your two groups, but you did not find one. Often that can happen in circumstances, for example, of small sample size. So that's kind of that on the vocabulary. You just may want to review that before the boards. I want to briefly mention non-parametric tests. These are mathematically quite complicated, and I always have to sort of look them up before I'm going to use them or consult a stats person, but I just want to mention them so that you know they exist and they're out there. So non-parametric tests are the statistical tests that you use when the data in your study are not normally distributed. So all the statistical tests that we talked about last year, t-tests and ANOVAs and chi-squares, are all to be used when the data are normally distributed. They all have sort of an alternative test that can be used when the data are not normally distributed, and the data are more likely to be abnormally distributed, let's say. If there's a small sample size, that's by far the most common reason, or if there's like a recruitment bias. I tried to think of a good example of this, and the example I came up with, which isn't great, is you're recruiting for a study on arthritis. You're looking at the incidence of arthritis in people, and you think, well, arthritis is more common in old people, so we think that the mean age in our study sample of people with arthritis is going to be 70, say. But you recruit your study at the YMCA, and as it happens, older people at the Y, of course, are less likely to have arthritis because of whether they be exercising otherwise. And so it turns out that your mean age is not 70, it's actually 50, and that screws up your data. So something like that could lead your data to be not normally distributed, but most commonly it's because of small sample size. So this is just a brief graph. You'll see down the left is the type of variable. The middle column is what you studied in first year EPH, so the type of parametric test that's appropriate. And then on the right column is just the name of the corresponding non-parametric test. And you do not need to know how to do these. They're quite complicated. But just so you've seen the names and you understand what they're for, so that if anyone mentions them, you'll understand sort of in what situations they can be used. I'll tell you that basically mathematically what they do is, instead of presupposing that the data are normally distributed around a mean with appropriate standard deviations and factoring those things into the equation, with small sample sizes they actually just individually deal with each data point. And that sort of obviates the need for there to be a mean and standard deviation and all that. In all circumstances, the non-parametric test always works. So like if you were stuck on a desert island and you didn't have a t-test, you could use the Wilcoxon rank sum test. It's just that the bar to show statistical significance is a bit higher. So if your data are normally distributed, you usually want to use the test that's in the middle column because it's easier and more efficient and it's easier to show a significant result. But in all cases, the parametric test will not work if the data are not normally distributed. The non-parametric test will work in either setting, normally distributed or not. Just take a quick peek at this, know the name, and know sort of when you would use them. I don't think it's going to get any more involved than that. Okay, survival analyses is a new topic that I want to talk about briefly. Survival analyses are a different way of looking at data. So we talked about logistic regression and linear regression. Survival analyses are a time to event model. So when you want to know not only did something happen, yes or no, but how long until it happened. So these kinds of analyses are particularly done, for example, in chemotherapy studies, when you not only want to know, like, did people die or not, but what you really want to know is people on this drug lived 36 months longer than people in the other group. And that's important data in some settings, not only with death, but in certain studies, like our department is doing a lot of work on hospital readmissions, and we want to know not only did people get readmitted to the hospital or not, but how long did they go until they got readmitted. In behavioral change studies, lots of times you want to know how long people kept the weight off, or how long people were able to stay with smoking cessation until they went back and smoked again, those kinds of things. And the statistical test that's applied is called the Kaplan-Meier curve. I'm going to show you a couple of these graphs in the next few slides. So here's an example of a survival analysis, and the different colors represent different groups. Across the bottom axis horizontally, you'll see time. So pretend that this is days, say. Every time the line, so look at the blue line, for example, the bright blue line. Every time the blue line dips down vertically, that means that a certain number of people in that group had the outcome or were lost. So either they died or they got readmitted to the hospital or whatever the outcome of interest was. The language that the Kaplan-Meier people use is they say they were censored at that point. That's a nicer way of saying they died or had the outcome of interest, right? So people were censored at a certain point. So you can see, like, for example, if this was a true survival study, you'd want to be in the pink group or the red group because those people are living a lot longer than the people in the blue group and the turquoise group. Here's another one looking at survival distributions by gender, and you can see that it's percent surviving on the y-axis and survival time in days on the x-axis. So if you looked at the study at the end of it and you just looked at yes or no, how many people died, I don't know that you'd see a significant difference between men and women, but at every point along the time, there were more women alive in the study. It took them longer to die as a group. And so, again, this is just an interesting way of looking at data that's time dependent to see if there's a difference between the two groups. The last thing I want to talk about is this intent to treat versus per protocol analysis. It's a different way of looking at analyses in clinical trials. We sort of brought up situations where this can be used in first year EPH, but I didn't actually mention this as a solution just because, again, we didn't really have time. So I'll just explain the difference between the two and then we'll do an example. A per protocol analysis means at the end of the randomized clinical trial, so one group gets the drug, the experimental drug, say, and one group gets placebo. At the end of the trial, we only analyze data from the subjects who completed everything and adhered to the protocol 100%. So they took the drug every day as prescribed, and they did everything they were supposed to do, and they stayed in the study till the very end. We only analyze data from those people. If they didn't do that, we throw their data out, right? And that way of analyzing the data is considered more pure because you really have a chance to see whether people who stuck to the protocol versus people who got control, whether there's a difference between the two groups. There's this other analysis called intent to treat, in which everyone who was enrolled is analyzed, even subjects who didn't take the meds every day, even people who dropped out a couple months before the end of the trial, even people who, ate stuff that they weren't supposed to eat in the trial or broke the rules. A lot of this is considered more realistic. It's less pure. The analysis is less pure, but it's more realistic. You can imagine that it would be harder to show a statistically significant difference between the two groups if you did intent to treat, right? Because there's more likely to be contamination and other factors and sort of noise between the two groups. So most journals want you to do intent to treat because it's sort of harder to show a result that way. So if you can show a result with intent to treat, then you're golden. If you can't, then some people will then do a per protocol analysis to say, like, look, we had a lot of people that broke the rules in this study, and the ones who didn't break the rules really showed an effect. So this can be a way to deal with bias, which I'll show you on the next slide. So here's an example that was actually on your EPH exam last year. Let's look at a smoking cessation intervention in a housing project in urban Boston. There were 500 people randomized to two arms. They either got a telephone counseling intervention to try to quit smoking or they got nothing. At 12 months, 100 people have been lost to follow-up from the intervention group. Only 30 people were lost to follow-up from the control group. So this is a question about differential loss to follow-up, right? And this is a potential source of bias because what you worry about is that people are more likely to be lost to follow-up if they went back to smoking and they were like too ashamed to tell you, right? And so you worry that so many more people were lost from the intervention group. So here's a table showing the results of just the people that stayed in the study, okay? So the intervention group has now 400 people in it. The control group has 470 people in it. And I did an odds ratio for you and showed that the intervention was 1 times as likely to be effective for smoking cessation compared with the control group. Okay, so 1.9 times, meaning the people in the intervention group were almost 2 times as likely to quit smoking as the people in the control group. This is a per protocol analysis. This is the intent to treat analysis. So there are different ways to deal with this, but the most conservative assumption is to assume that everyone who was lost to follow-up resumed smoking. So we put them all in the did not quit group. So the quit smoking column is the same, but the did not quit column has more people in it because we added 100, and then we also added 30 people from the control group, okay? And so the odds ratio here is 1.7, meaning that the people in the intervention group are 1.7 times as likely to quit smoking compared with people in the control group. It's not quite as strong a result as the per protocol analysis. You can envision there might be a study, for example, where when you do the intent to treat, you actually don't get an odds ratio over 1. So we're done. I just want to remind you that you will want to briefly review epi and biostats for step 1. It won't be a large portion of step 1, but it should be pretty easy for you to nail the questions correctly if you just spend, a tiny sliver of your time studying for this. There's a couple places to find information. The first aid books are pretty good. The Blackboard website for our course last year should remain open to you this year, so you can re-watch some of the webcasts as needed, including this one, which will also be on the DRX Blackboard, and I'll put it on the old EPH Blackboard site as well. I'm always available for questions. Don't stress about this part of the boards. It shouldn't be that bad, but I just wanted you to have the information that you need. Good luck.